This is another lesson on areas and distances. If a train moves along a track at a steady rate of 75 miles per hour from 7 to 9 a.m., what's the total distance traveled by the train? Well, we know rate times time equals distance. The time from 7 to 9 is 2 hours. The rate's 75, so 2 times 75, or 150 miles, would be the distance. But notice that that's also the area of this rectangle. So we can actually use area to find distance. Isn't that interesting? Distance equals rate times time, which is also the area under the curve, what we did yesterday. It doesn't matter if it's a rectangle, if we've got some goofy shape here along the top. We can still find the distance along here for the period from A to B by calculating the area under the curve. How do we find that area, though? This is a trickier area to find. Well, we can estimate it by cutting this up into little rectangles, and the more little rectangles we cut it up into, the more it looks like little rectangles, because this top doesn't look like a rectangle. But if we get them really infinitely thin or skinny, they'll look more and more like rectangles at the top. So we can also do approximations, where we have what's called the left-hand approximation, rectangular approximation method. So if I go left-hand, notice how I've got, I stay below the triangle, or the curve here. I can do the midpoint rectangular approximation method, where the middle of the top of the rectangle is on the curve. So some of it's outside, some of it's untouched, some of it's outside, some of it's untouched. And I can do right hand, where I'm always doing an overestimate here. So there's 3 different values. Left hand is always going to be less than. At least in this case, we're getting less than. I wouldn't say always, because what if the curve comes the other way? Right hand in this case is giving me a value that's greater. And midpoint, well, it's hard to tell which is greater and which is less, but it's not exact. It's an approximation. In this approximation, we've got a left-handed rectangular approximation. If I do 6 intervals, 1, 2, 3, 4, 5, I'm also looking at this flat one here, 6. If I calculate the areas of all the rectangles, notice how they're all 1/2 wide and they have different heights. One of them's 0 high, one of them's 1/2 high, one of them's 1 high, and so on. I get about 6.875, not about, but I get 6.875. If I go to midpoints, I get 8.9, etc. And if I go to right hands, I get an overestimate of 11.3. So I got 3 different values. But what if I, instead of just doing 6 rectangles, I do 12? Notice the numbers seem to be getting a little closer together. When I do 6 rectangles in each one, the numbers were farther apart than they are when I did 12. Look down here at 100. The numbers are getting even closer together. At 1,000, the numbers are getting closer together. In fact, the more rectangles I use, the more each approximation starts becoming the same number. Interesting, isn't it? That's our learning target for today. I'll see you in class.